So thank you for the introduction. Yeah, so nuclear was a bracket on the MCA chart yesterday. It was in a bracket as a potential thing we should consider for the future. So I guess the next 20 minutes, I'm going to talk around where nuclear technology is at the moment and what we see as the potential for nuclear for decarbonising generally, but obviously specific to today for the marine sector. So it might not be a solution for today or tomorrow in the maritime sector, but we need to keep our minds open, I think. So if you take anything away from this, it's we shouldn't write nuclear off because it's not petrified sunlight. It is actually sunlight. E equals mc squared. It's the most power-dense energy source we have on the planet, so we shouldn't dismiss it. So, just a quick introduction, quick overview of Rolls-Royce. You're probably aware of what we do, but if you aren't, here's an overview. So, we're a multinational, UK headquartered engineering technology company. We produce power systems. So, civil aerospace, large gas turbines, small gas turbines for civil aerospace. We have a power systems division. We have a colleague here from Power Systems today covering reciprocating engines for multiple markets. And we have a defence sector, so kind of a government-focused sector with multiple products within that sector, including nuclear. So our nuclear experience really has been in that defence sector. So for the last over 60 years, Rolls-Royce has designed, manufactured, maintained and supported the Royal Navy nuclear submarine fleet. So multiple reactors over the last 60 years, and there's 11 nuclear submarines somewhere around the UK or on deployment with a Rolls-Royce reactor as we speak today. But we don't just do submarines. So over the last nearly a decade now, we've had a small modular reactor business. So that business has just last year secured just under £500 million of funding to commercialise that design, small modular reactor design, and take that to market and deploy those systems this decade. Bit more on SMRs later, because they're not that small, but they could be a solution to some of the things Oscar was just talking about, that providing that zero carbon energy to produce some of these new fuels, some of these new e-fuels. And then we've got nuclear innovation. So that's all the cool new stuff that me and my team are privileged to work on. And I'll dive into that a little bit, well, through the next 20 minutes, because nuclear technology is evolving, and there's some really, really interesting new techniques and manufacturing techniques that really do change the kind of the safety aspects of new and future reactor designs. So I won't dwell on this, because I think we've heard a whole day and no doubt another day today on the need for change. So so I won't dwell on it, because I'm telling you things you already know here. I was reflecting last night with some colleagues that this could equally be an aerospace conference. I've been to aerospace conferences that are pretty similar in theme and tone to this conference, or even power generation. There's an existential threat of climate change, and this industry is no different. So there is a clear need to do something different, and we clearly believe nuclear power can at some point play a part in that. So micronuclear, what is micronuclear? That was the title of the presentation. This is just to put it into perspective, really, of what we mean by micronuclear. So this is a portfolio of nuclear products that Rolls-Royce are involved with. I've talked about this. I'll go kind of right to left, left to right. We'll start big. So I talked about the Rolls-Royce small modular reactor design. It's not actually that small. It's nearly 0.5 gigawatt of electrical output, 470 megawatts-ish. So it's not that big. It is pretty big in terms of power output. It's small in terms of footprint, and it's factory built and deployed as modules. So it's small compared to the huge plants at Hinkley Point C and those kind of things that we've known in the past. But in terms of electrical output, it is actually quite big. Moving down the scale, so submarines, I've not put a number on here. It's kind of a bit of a range for obvious reasons, but in the tens of megawatts. So still a reasonable sized plant on those submarines. And then we move into micro-reactors. So what we mean by micro-reactors is something between, as it says on the screen here, anything really between a megawatt and 10 megawatt electrical output. And they, in nuclear terms, really are micro. At that 10 megawatt electrical output, we're talking about the volume footprint of a 40-foot ISO container. So a pretty small, compact reactor plant producing 10 megawatts of electrical output. And then, kind of at the small scale, some of the kind of really interesting stuff that we do in nuclear innovation in my area is nuclear power for space exploration. So RTGs, decay heat, so radioisotope thermoelectric generators at the very small end, so then the kind of single kilowatts range, and then really small micro-reactors, so a megawatt and below, make them lightweight, and they're perfect for space exploration and powering future moon bases. Which sounds ridiculous, but NASA have live design contracts to do exactly that. So it's, as with everything, I think, micronuclear is not a new idea. I think the 60s would have been a fantastic time to be a nuclear engineer. You see the similar dates on all of these things. So as a kind of bit of a tour of previous micronuclear reactors, the US tried everything, I think, in the 60s. The US Army had a deployable reactor, so 0.5 megawatt electrical, on the back of a lorry. So this thing up here. And they built that, they operated it. Yeah, funny things, no new ideas. The US Army have currently got a design contract to design and deploy a prototype of a shipping container on the back of a lorry micro-reactor by 2025. Rolls-Royce North America are part of that team. They didn't stop there. They went a bit bigger, 2 megawatts, not quite on the back of a lorry, but it's still pretty small. This was another reactor the US Army deployed in the mid-60s, and that powered a remote base on Greenland. They also sent a nuclear reactor into space in the 60s. So this was a very small reactor. This top portion here is the actual reactor itself. This is a radiator for getting rid of the excess heat, but a tiny reactor that the Americans did fly into space. So they stopped there with the space nuclear program. As I said, they're just picking it up actually again. But the Russians didn't. The Russians used nuclear reactors to power reconnaissance satellites through the 70s, 80s, into the early 90s. There's 30 nuclear reactors. They're all shut down, but they're still in orbit, orbiting the planet today. And then absolutely fascinating, if you're a submarine geek like myself, Naval Reactors 1. So this was a Rickover special. They built a very small submarine, nuclear powered, so it had a very small, around 5 megawatt reactor, and they put it in a very small submarine. So a crew of about 6 or 8 people, very small submarine to go and do quiet things during the Cold War. And that was there's an incredible book around this submarine called Dark Waters, if anyone's interested. But it was the most highly utilized submarine in the US fleet. And it operated from 1969 all the way to the early 2000s. Absolutely fascinating. But proves, and I guess all of these prove that making a nuclear reactor small is totally possible, totally feasible. So I talked at the start around some, some technological advancements that have happened since all these cool designs in the 60s. So I really want to dive into that because that unlocks, from a safety aspect, why we believe that nuclear can play a part in decarbonisation in the future, and not just the big plants, so not just the SMRs of the world, but small deployable systems for multiple applications, including marine. And the first thing I want to talk about is the nuclear fuel. So historically, nuclear fuel, you get your uranium and you put it into a metal matrix, and you either make some plates out of it or some rods out of it, and then you clad it in another metal, usually zirconium, and then you put that into your reactor core, and you have to operate that reactor to make sure that you don't go above the melting point of that clad, because the clad material is what keeps the fuel and the fission products, so the radioactive isotopes that you create when you break uranium in half and create the energy, you have to keep all those within the clad. It's really good if you keep it in the clad. But those cladding materials, kind of zirconium, relatively high melting points, but only relatively high melting points. So current reactor designs, there's a lot of safety systems, active safety systems, passive safety systems, and operational constraints that ensure you don't go above the melting point of that clad. Why I get really excited about some of this new technology is because the industry is coming up with new manufacturing techniques, really, and new materials, or using new materials to get rid of those constraints. So tristructural isotropic fuel is a real game changer in the nuclear industry. It's what this fuel forms, the picture here, you have a kernel of uranium, so uranium carbide or uranium oxide, and then you cover this small particle in concentric layers, a bit like a peanut M&M, if anyone likes peanut M&Ms. Cover the fuel in different layers. So there's a porous carbon layer to just absorb any fission product gases, make sure you don't overpressure from the inside these small spheres. And then there's a pyrolytic carbon layer, pyrolytic carbon is super hard stuff. They put it on the re-entry nose cones of missiles and things like that. Really, really tough stuff. And then silicon carbide, so a ceramic, very high temperature resistant material, and then another pyrolytic carbon layer on the outside. Sounds great. What does all this mean? It basically means that under any temperature excursion or accident scenario, you can't melt or damage or break these particles. They're incredibly tough little particles. In terms of size, they're quite small, so about 500 microns, so they're pretty small particles. And it's really the manufacturing process to get the repeatability and the reliability of these coating layers that has advanced over the last, say, 20 years, to the point where this fuel is, there are several organizations that can manufacture this fuel. The National Nuclear Lab in the UK, up in Sellafield, has the capability to, they are developing this fuel, they can make this fuel. And there are programs in the UK and also a bit more advanced in the US that have been irradiating and testing this fuel in nuclear reactors. So this really, really is a game changer for nuclear power. It's an overused term, but this really is. It essentially means, under any accident scenarios, you keep your fuel and your fission products in one place, and that's huge. Some other advancements in nuclear technology, really coupled with a fuel form like this, mean that we can package these nuclear reactors, take advantage of the containment of that fuel, and start thinking about new applications for nuclear, where you don't have to have a huge containment building like traditional nuclear reactors because of this fuel. So some of the other stuff I just want to mention is micro-turbines. So Rolls-Royce are pretty good at turbines. It's our core business, really. There's been quite a lot of advancements in shrinking down the power density of those turbines. So this thing here, it's not actually Rolls-Royce designed this, but it's amazing. This is a 10 megawatt supercritical CO2 turbine. 10 megawatt. I mean, supercritical CO2 is probably not what we'd use, but it just shows that you can really, really shrink down some of these power generating devices. Absolutely incredible. And then another thing I want to mention is I talked about active and passive safety systems for nuclear reactors currently. Cooling a nuclear reactor is a really good thing to do. Keep it nice and cool because of the clad that I talked about earlier. However, some of the legacy designs have used pumps, as you'd expect, fluid systems to cool those reactors. And they're great until you lose your power and you lose your pumping capability. Then you need other systems, redundant power systems, etc. So this guy over here, this is a guy in NASA. So NASA, in conjunction with Los Alamos Nuclear Laboratory in the US, built a totally passively cooled reactor and critically tested it about 2 years ago now. So what this is, a very small reactor core down here. I mean, this is a model, but they did build this. Very small core, and then these are the cool things. These are liquid metal heat pipes. So a heat pipe is a really, really efficient way of passively transferring heat. So they're sealed tubes with a very small amount of working fluid within them and a wick structure. At the hot end, so in the core, the fluid evaporates, travels to through natural circulation, travels to the cold end where it's condensed, and then the wick structure through capillary action pulls the working fluid back to the hot end where the whole process is repeated. And they're incredibly efficient because you get the latent heat of evaporation and condensation. So they're incredibly efficient at removing heat, and they're totally passive. So every laptop at the moment, no doubt all got a laptop, every laptop has a copper water heat pipe in it to remove heat from the motherboard. Excuse me. So very high TRL technology. The really exciting thing that NASA and Los Alamos did was use those heat pipes. It demonstrated those heat pipes in an actual nuclear reactor test. So really, really exciting stuff because it's totally passive. So unsurprisingly, I did say I'd talk about our micro-reactor design a little bit. Rolls-Royce and the nuclear innovation team are developing a small micro-reactor to do exactly what I've just said, 10 megawatts from a kind of 40-foot ISO container. It's a TRISO-fueled core, as you'd expect. Big fan of TRISO fuel. And it uses liquid metal heat pipes to transfer the heat from the core to a set of small turbines to generate that power, all in the footprint of a 40-foot shipping container. And we really believe that for certain applications where deployability, energy security, high base load, and long life will be absolutely key applications that these solutions can meet. So this is a little bit like one of Oscar's charts that he showed before. So we've been looking at, so we're nuclear designers, we're not ship owners. So we've been looking at what applications are best suited to a solution like this, really from an economic lens. So we're reactor designers. We can design and are designing a small modular reactor and a small micro-reactor to get 10 megawatts out of a shipping container. Excuse me. I'm just going to get a drink, actually. So this is a bit of a busy chart, but what it shows is basically the cost comparison of a diesel generating system compared to a reactor over its lifetime. So in the middle here, so 3 scenarios: a 5 megawatt reactor with a 5-year core life, 5 megawatt reactor with a 10-year core life, or 10 megawatts, 10 years. So if we just take this middle case, so 5 megawatts over 10 years is 438,000 megawatt hours, assuming baseload power production. They're the kind of applications that really lend themselves to nuclear. The equivalent, so diesel is about, you get about 3 kilowatt hours from a litre, there or thereabouts. So the equivalent fuel in diesel terms to that nuclear reactor is 146 million litres of diesel. Taking a pretty broad range of price of fuel, and it is broad range, that's equivalent to 292 to 1.6 billion pounds just in fuel costs. So we're using economic evaluations like this to really understand where nuclear can play a part and can be economical and actually cheaper than incumbent technologies. Because if it isn't, it's not going to be sustainable from an economic point of view. So just a few examples there where, you know, baseload power and applications that really lend themselves to requiring baseload power are perfect for nuclear solutions. So a few examples here of what those applications could be. So I'll start in the middle. Oscar talked around making sure that the power for your power-to-X fuel is renewable. Otherwise, what's the point? So, you know, synthetic fuel production and hydrogen production, providing the heat and the power for those applications, would be a really good fit for a micro-reactor in a remote port. And I'm conscious of time, I won't go through all of these, but you can see wherever you need high baseload power in a remote-ish locality, then these reactors can really fit those applications and be economical. So I'll kind of leave it there, and as I said at the start, if you take nothing from this but one point, it should be that, you know, nuclear technology is evolving, and we really shouldn't ignore nuclear technology as one of the, there are no silver bullets, but as one of the potential future energy sources for zero carbon shipping.